Welcome back to the lecture on computer-aided design and manufacturing. We are more focused towards CAD in this lecture. Last lecture we saw more towards generic, simple 2D representation in CAD, and then we slightly extended how from 2D to 3D has to happen. In that case, we started talking about translation and sweeping, two mechanisms or two algorithms which are inbuilt in 2D such that you can create 3D structures. We also saw a simple parametric form wherein which you draw a 2D structure and then you sweep it. For example, if you can think of a plumber block. So, those people who are not aware of a plumber block, the schematic diagram looks something like this. Okay. So, you put a bearing inside. So, here if you draw the 2D structure and if you just extrude, because it is going to be along the z direction the same. So, you go here to whatever distance it is and correspondingly you also make the circular also there and then you try to get it. So, this one along the z direction whatever you pull, from the 2D structure we get a 3D object. So, such simple things we were discussing, but life is not as easy or as simple as we think. We moved into we have to now move into 3D structures. In 3D also we will have free form, which is the need of the hour, because today we are looking at multi purpose or multi application or multiple functional doing components which are used in the products. So, keeping that in mind, we will move through this lecture. So, in this lecture we will try to see Kuhn surfaces, then move to Bézier curve, B-spline, constraint based modeling, then we will see wireframe modeling and then different types of solid model, then constructive solid geometry in the 3D form, then feature recognition and designing. In that we will try to see feature based design and feature interaction. So, when we talk about freeform surfaces, first thing comes Kuhn surfaces. So, Kuhn surfaces are relatively simple, a next step from whatever we have studied 2D and then we saw translation, rotation, and next step moving towards 3D is going to be with freeform, and in 2D also freeform surfaces is very important. So, we will see how to draw a curve and other things. So, Kuhn surface is basically a simple surface which can be represented, which can be described by means of simple formula. So, in reality you will have many surfaces which these surfaces has to be drawn. So, what we do is we try to divide the surface. The easiest thing is we will try to divide the surface into small patches, okay, and which is defined by a network of curves. What we get is a Kuhn surface. For example, so this can be P01, this can be P00, this can be P10, this can be P11, and you can define the functions, and you also define the directions with which the curve has to move. For example, here you can put it as PU0, PUV, and then you will have P u comma 1. So, you have seen now you have discretized this curve patch into several small points, and then you are trying to represent those points. So, this is a cone surface. So, generally in cone surface, each patch, the entire patch is parameterized. So, parameterized by interpolation, by filling or by interpolation. By interpolation, we try to get those boundaries and then we try to solve. Next, we will see the Bézier curve. Those curves which we saw earlier also had some technical problems. So, wherein which you define certain points and you defined a complete patch. So, all you have to do is wherever you wanted to attach it or fix it up to a free form surface, the entire patch is been already defined. So, that patch comes, you fix it up and then you start getting the smoothing of the curve. So, when we look into the patch also, we had limitations that we were not able to control and change those patches. So, then came the need for going into Bézier curve. Okay. As far as Bézier curve is concerned, if we wanted to draw a curve wherein which we know the starting point, ending point, we define some more control points and try to draw the curve which is close to those control points. So, those options are given by this Bézier curve. So, currently we are discussing 2D, we also have a similar one for 3D. So, Bézier curve is nothing but a curve that uses that is used in 2D graphical applications. Okay. The curve is defined by 4 points. They are start point, end point, and 2 separate midpoints. Okay. The third thing is the shape of a Bézier curve can be changed by moving the control points. So, Bézier curve uses a vertices as a control point for approximating the generating curve. The curve must pass through first and last point, that is compulsory, with all the other points acting as a control point. So, you do not have to pass through it, but these control points the curve has to go close to those control points. Now, you see various examples of Bézier curve depending on the associated control polygon. So, you had a start point, you had an end point, then you had 2 points which we have designed, which we have defined, and then the curve moves along this path. So, suppose I define P0, P3, but change the location of P1 and P2, then I get a Bézier curve of this shape. I have just changed the control points, but the start point and end point are approximately the same. The next one is I have used the same starting point and ending point, but still moved the P1 to this side and P2 somewhere here. So, you see a completely different curve profile coming. So, as far as application point of view is concerned, the control points decides the curve profile. So, there is a modification of the Bézier curve by tweeting the control points. You can change the curve, okay. And here what happens is, you can see here I have just moved a control point from here to slightly here. So, this portion of the curve is tweeted, but it is not only this small patch, but corresponding to those patch all other points are also moved. So, it will have a starting point and it will have an ending point. Okay. So, the modification of Bézier curve by tweeting the control points, you can try to tweet the complete curve. The next advancement, so I don't wanted to control, I wanted to control at as closely as possible. So, what limitation was there in Bézier was removed by using B-spline. In the case of Bézier curve, it is a single curve controlled by all the control points. It is only a single curve. With an increase in number of control points, the order of the polynomial representing the curve increases. So, if you want to have more and more and more control, so what you have to do is you have to keep increasing the number of control points. B-spline generates a single piecewise parametric polynomial curve through any number of control points with the degree of the polynomial selected by the designer. So, you look at it, you see this is a B-spline curve. So, you see here it is now divided into several small patches. So, these are the control points, these are the control polygons. So, what was missing in Bézier could come out easily with B-spline. Why is this all important for this course is, when you want to do anything in digital manufacturing, you are supposed to draw. When you are supposed to draw, you can have simple geometries, freeform surfaces. In freeform surfaces, the major thing is going to be the curve. So, in curve, if I give you the freedom of tweaking the curve to your own requirement without putting any constraint, then that is what will try to be a major advantage for the designer. Why is this required? Because when you are looking for the mass customization point of view, you are supposed to understand the customer's requirement in terms of design and make changes in the design such that it can suit the customer's need. For example, you can have a standard shoe, and in that standard shoe you can have modules which are added to the shoe such that it can suit to the customer. Currently, you can see lot of people who have issues in their leg, or if they have movement. For them, what we do is we currently make customized shoes, but these customized shoes are also not truly customized to the customer requirement. So, what they do for those people is, either if there is a height variation, the modules are added. These modules are then carved to the requirement. So, when you have to carve it and get this carving done automatically, then we are supposed to get to this freedom of using this Bézier B-spline curves. So, B-spline generates a single piecewise parametric polynomial curve through any number of control points, these are the control points, with the degree of the polynomial selected by the designer. Here is a lofted surface. So, this lofted surface, these are the curves, these curves are joined together and they form a surface. So, all these curves can be drawn by using B-spline. So, where in which you had these control points, what we saw in the previous figure. So, you see the control points, and these control points are used to decide the curve. So, when we real time draw these objects, we draw this is a simple object, or this you can use it as a you can have a simple primitive is there. These primitives are chosen and these primitives are placed at locations. But when these primitives are placed and when this butts against a flat one, it is always necessary to have a filleting done such that these points are not the stress concentration points and you can keep continuing this. If this is a flat one which just butts against a surface, then this will lead to a failure very fast. So, here what we do is we have a option of filleting. You can see here wherever there is a sharp edge, there is an option of filleting. Filleting is giving, this will try to enhance the safety as well as the life of the component. So, these are some of the examples wherein which filleting or blunt methods for model generation is possible. When we start talking about a real time application of a car, so the example of a tweaking method for surface modification is very much used. So, the radius need not be uniform. You can have some radius change at several points. So, if you want to do that, now what you do is you discretize them at several points and you are given the freedom of changing or placing the control points and changing these patches. Okay. So, it will look as though it is smooth, but when you watch very closely you can see several small facets are there or curve structures, because they have discretized the curve into several small control points. So, this is what is talked about in this B-spline. So, you have control points and you have control polygons. When we talk about this constraint based modeling, so in this type of modeling often called as parametric modeling or constraint based modeling, most of the time the model starts with a 2D sketch and then swept along the direction so that you get a 3D object. This is the same thing what we studied in the 2D with sweep command. So, there it was a simple object. So, here it is a completely real time object. So, what you have done is you have constructed this 2D and then you say desired depth, which we make 3D and then you get the component. So, the constraint based modeling, the sketch which is fully constrained and dimensions are given here. So, these are the dimensions which are given. So, you can also try to establish a relationship between all these angles as well as the side edge length, and you can define it as a library function, and all you have to do is define some 3-4 points, and then moment you define these 3-4 points, the rest of the object is getting constructed. So, in constraint based you do a 2D and then you stretch it either in the positive direction or in the negative direction, you get a complete object. So, when sweeping along a linear path is produced, the solid is made. So, in this constraint also, if you want to cut and remove material, so that is also possible. For example, I do not want this portion, I want this portion to be cut down. I give the 2D profile and then I say along this direction stretch it and then do this is A, this is B. So, then I say subtract B from A. So, what you get will be this profile. So, a solid after execution and extruded cut of the geometry, you will get this. So, these are all part of constraint based modeling, which is defined from 2D and then you start doing 3D operations. If you take an object like this and for the same object what we were discussing prior. So, now, so here I want to make a hole, here I want to make a hole, and then here I wanted to fasten. So, this object I draw all these fellows and then I say subtract these things, you get to see the final object. Okay. The final solid is this what you get. So, this you can see it can be quickly made through constraint based modeling. A geometric modeling created following the sequence of features as shown here. First we create a box, then we create a hole and then we create a shell. What is shell here? Shell is a subcommand that converts a 3D solid model, solid, into a hollow shell with a wall thickness of desirability, or it draws it, this is the shell, whatever we talk about, okay, shell, box, then we have a hollow, then we have a shell. Shell is nothing but a sub command that converts a 3D solid into a hollow shell with the wall thickness of a known wall thickness. So, feature based model and its modification. Feature, so this is the base feature and this hole is another feature. All you do is you take the base feature, take the whole feature and define the locating points, then you get whatever you want. So, if you want to make a slot, slot is a third feature. You define the location for the slot, you get the slots on both the ends. So, you again take the base feature and then if you want to make holes, you try to take 5 holes, you put one after the other and 2 slots on the both sides, you try to get whatever you want. So, now the feature of slot is known to me, the feature of hole is known to me, the base feature is known to me. I only put the location for these features in the drawing such that I get whatever I want. Okay. This is again a constraint based modeling and here it is feature based modeling and its modified form. Why is this important? Because I know to create a slot, I know to create a hole, right. So, when I say I know to create a hole, I know the list of process parameters, I know what is the machine to use, what is the process parameter to use, what are the toolings to be used such that I get the output. So, now when I say hole as a feature, so now immediately when I draw the CAD for the CAM, it is easy for bringing in all the manufacturing processes attached to it and allied to it. Okay. So, we have here in this particular case, we have distinguished different features and linked with these features to the manufacturing process. The other modeling methods are cell decomposition. We will see little later, but however, when we say cell decomposition, what we do is we draw the entire cell, or it is like a graph paper, we draw entire graph paper and on the graph paper we start drawing an object. Okay. And here the object is decomposed into several cells and then we know what are all the cells to doing. So, if you look at very good artists, what they do is they always draw a grid pattern in their artistic paper and then they start linking it in generating the feature whatever it is. Then we will also see what is variant type, symbolic forming and symbolic programming and form features. So, this is a variant method of modeling. So, here in which we define x1, x2, x3, x4, x5, 6, 7 and 8. And now, this x1, x2, x3, x3 all these things are having some relationship and already this relationship is established. So, all you can do is just drop in these values and try to get different shapes and size of this same component. So, that is a variant method. So, we just put these things to the requirement. And again as in cooking also we can scale, when we scale up the processes also change. In manufacturing also when we scale up from 10 parts to 20 parts, 100 parts, 1000 parts, the manufacturing process also changes. So, that is a separate domain, but we are not getting into the domain, we are talking only about CAD. So, CAD there is a relationship clearly established between these variables and when you call this product or component comes in front of you, you just define it and then get the part. So, this is a variant method of modeling. The other one is symbolic programming. We use symbols. It is like trying to tell a blind man how do you walk and then generate a path for him so that he regularly follows. So, you look at the component is this, for which the component is divided into several lines, arcs and curves. So, now these curves have to be generated one after the other. So, that is what is done using the symbols here. So, we use top, bottom, left, right, okay, and then between top and you can say north, south, and then you call it as east and west. So, this is northwest, northeast, southeast, southwest, right. And now what you do is you try to use those buttons and then start defining a sequence. So, here the sequence is defined, the component is made, the dimensions are not talked about here, the dimensions will be talked next. Okay. So, here if you see first part, it moves from here, this is first, then this goes, and then it goes for a chamfer 3, and then it goes for a chamfer, then it goes down. So, this is 4, and then it is 5. So, you can keep on adding the sequence. This is the key sequence to generate the process. These are the symbols. With these symbols, you can try to draw this component, and this component you can start feeding the dimensions and get the data. The examples of form features, this is an example. So, this is a feature. From this feature, what are all the features from the blank to what are all the features you want to make, you can try to draw it and then try to store it. So, when we move to wireframe, though we know wireframe does not give you a unique representation, but wireframe is exhaustively used because it occupies a small space. And when we talk about wireframe, we will first always start defining a point to a line to a circle, and then arc. So, if I know to draw a point, good. If I know to draw 2 points, it is excellent. Then I can join these 2 points by a line. So, point 1, 2, then it becomes a line. Then if I want to make a little more difficult, so point and point. So, I make a circle. Okay, this is the radius or the center point. Okay, and then the next one is the arc. So, arc is important because here I am given you the freeformness. So, if I know to define a point, a line, a circle and a freeform arc, okay, so then I can draw any complex objects. So, in wireframe we will see how do they represent these parameters or these entities, drawing entities. So, point, you can define a point a, x, y, z. You can define a line and then you can say start point and midpoint like this, and this is for a circle, this is for a sector you want to do, and a point drawn at an angle to x axis. So, these are different ways you define a point, and these are different ways you define a line. Point and point join A and B, you get a line. So, you draw a parallel to this line with an offset of this also you draw a line, and say a perpendicular to this you can draw, you just define the distance, and then you can also try to draw a line which is a tangent to the circle. So, and for a single circle, a tangent between two circles. Okay. So, if you look at belts pulley mechanism, you have crisscross where the tension is maintained. The other one is you can define circles by giving center point and radius. So, center point and a point here, and then you can define 3 center points. You can define a center point and a tangent to, you can define 2 lines and then tangent to which is intersecting. So, you can also define that R, and then you can also define with the other circles, and then 2 circles, joining these 2 circles a radius. So, you can define a circle. These are all different ways of defining a circle. So, then let us define an arc. So, arc I have already told you start point, end point, midpoint, start point, end point, and then you can fix the center. You can also try to say start point, end point and the angle of including this is start point, end point, where I have said the start point, center point and the angle included, or I can say start point, end point and the radius. So, these are different ways of drawing an arc. in a wireframe representation, if we try to draw a cube, we would like to see how does this data getting represented. So, here the edges are these are the vertices 1, 2, 3, 4, and you just offset this plane, you get 5, 6, 7, 8. Okay. Now, this is 5, 6, 7, 8, you have drawn this. These are the edges, and now if you want to draw a line connecting that. So, 1 and 2 is connected by 1, 2 and 3 by 2, 3 and 4 by 3, 4 and 1 by 4, and in the same way 5 and 6 by 5, you are drawing a line. So, this when you look from 3D perspective, it becomes an edge. 6 and 7 it is 6, 7 and 8 it is 7, 8 and 5 it is 8. Okay. Now, these two planes are hanging in free air. You wanted a cube has to be linked between these two fellows. So, then what you do, you start dropping a line from each vertices. So, you get 9, 10, 11 and 12. Okay. If you want to represent this data in computer, this is how it is represented. So, vertices 1, 2, 3, 4, what are all the x, y, z? Then edge number 1, what is the starting point is 1 and the ending point is 2. So, here because you have defined all the vertices, you do not have to define once again the vertices here. So, what you do is you just say a edge is drawn connecting 1 and 2. For example, let us take 8, edge number 8 is this. So, it is trying to connect vertices 8 with vertices 5, vertices 8 with vertices 5. Okay. This is how a wireframe data is stored in a computer. So, all these things, cube is a simple 3D object, but what we saw, curves and lines and all those things are small basic entities which can be used to develop a 3D model. In wireframe representation, you have block, which is a cube example we saw. We can also have a cylinder and a cone. Suppose you want to define a cone, we do this: center point, radius, and then we also tell the height. So, you can try to get a cone. So, when we talk about curves, there are two ways of representing the curves. So, one is the implicit form, the other one is the parametric form. In implicit form, the curve is represented as f is a function of x, y, z which is equal to 0, g is a function x, y, z is equal to 0, but we do not have a linking thing between these two. So, we felt that if we can define f and g with minimum number of points, it will be good, and if I can also connect f and g through one more connect these two, interconnect with the variable, then that is much more easier for me to operate. So, I do not have to define so many points. So, in that case, the parametric form gave me an advantage. In parametric form, the curve is represented as x equal to x of u, y equal to y of u, z equal to. So, you see here all these things are linked by a terminology or by a factor called u. All I have to do is define u, which takes a value 0 to 1, I can get whatever output I want. So, here is a curve. So, I have defined point, start point, end point, point P1 and P2. Here is the u vector which is going. So, I can take a value from 0 to 1 anywhere and I can start drawing the curve. So, if you want to represent line, which is this is a simple equation in a parametric form, you represent it as x, y and z. So, now you see u takes a value between 0 to 1. So, when we have to represent a simple circle, it is x square plus y square is equal to r square. In the parametric form, I represent it as x equal to r cos theta, y equal to r sin theta, where theta takes a value between 0 to 2 pi, r is the radius. So, now you see in the parametric form, I am representing a circle. So, this is what it is. So, 1 and these are what it is, and if you want to see, these are facets which I have drawn. So, these are all facets, no? The arc is divided into several facets, right. So, this is the curve which is getting done. So, ellipse, the parametric form of an ellipse whose center lies at the origin of the coordinate system below is given by x equal to a cos alpha phi and y equal to b sin phi. So, this is phi a and this is b. So, this is a typical ellipse. So, you have x and y. So, parabola is y square equal to 4ax. One of the parametric form of the parabola is given by x equal to a u square and y equal to 2au, where u takes a value, this is very important, 0 to infinity. Since the parabola is not closed, so that is why we go to infinity. Since the parabola is not a closed curve like an ellipse, the value of u needs to be limited for the display purpose. When we want to do a hyperbola, the implicit equation for a hyperbola is x square by a square minus y square by b square equal to 1. I am representing it into a parametric form. I represent it as a cos h theta and b sin h theta. Okay. And so, here theta also tries to take the value like this, whatever is used in ellipse. Okay. But all these things are simple curves, but what we really want in our real time usage is free form curves. So, now apart from all these curves, there is a need for curve fitting also to happen. So, next we will see what is curve fitting. Often designers will have to deal with informations of a given object in the form of coordinate data rather than geometric equation, because we touch surfaces and we get the data, something like that. So, you see here this gets developed. Okay. So, here what we do is we cannot represent this form, which is a biomimicking form, in a geometric form. We always try to take several of these coordinate points, convert these coordinates and then get the value. So, in such cases it is necessary for the designer to use a mathematical technique of curve fitting. What is curve fitting? You have several points, pass the curve through, as such you are covering maximum number of points or closer to maximum number of points. So, the curve fitting to generate the necessary smooth curve that satisfies the requirement. Okay. So, the curve fitting is something which is very important. So, aerofoil curve fits with the data point. So, here we use Lagrangian polymer. A second order Lagrangian polymer is given below for fitting the 3 data points x, x0, x1, x2. So, this can be represented by this. On fine tuning this can be represented in this form. So, the method of least square is also used in order to have a best curve fit. So, since fx is an approximate curve and it is not passing through all the points of data, the error at any given point xi, yi is given by error is nothing but yi minus a function of xi. So, for example, you have several of these points and then you have a line passing through. Now, you wanted to measure this deviation, which is the error. Okay. Since fx is an approximate curve and not passing through all the points of data, the error at any given point xi, yi is given by ei is equal to yi minus a function of xi. The summation of all the errors will give an estimate of the total deviation of the curve from the points. However, since the errors tends to cancel out each other, sum of the squares of errors should be minimum. So, this error deviation should be minimum. Suppose you have a set of data points like this and you are trying to draw a line. So, now what I am trying to, a line or a curve, I am trying to shift this curve such that I try to have minimum error between the data points. So, in curve fitting method we have two methods, one is interpolation, another one is the best fit method. Interpolation is I know start point, I know end point, I know a curve and I know the function of this curve. Okay. So, in interpolation what we do is we discretize into several small points and these points are the curve, these points are discretizing the curve for which you have written an equation. So, it is necessary that a curve produced will have to go through all the data points. Cubic spline and Lagrangian interpolation methods are used in interpolation. Shape of the curve is affected to a great extent by manipulating a single data point. The nature of tweaking is unpredictable. So, these are the points for interpolation. When we go to best fit curves, the best fit will not pass through all the points which I told you, data point, curve. So, this fellow will get moved up or down to get the best, and the curves will not pass through all the points, but will result in a curve that will be closest to as many points. That is best fit method. Regression and the least square are two different techniques which are different techniques which are used to get the best fit curve. Bézier curve, B-spline we studied, Bézier curve falls in this category. So, what is Bézier curve? Start point, end point, control points, that is a best fit curve. So, false. It is possible to have local modification easily by tweaking a single point where the behavior is more predictable. That is the advantage of best fit. So, we would stop here. We will continue in the next class. Thank you very much.